Okay, as usual, I'm starting off with your electromotive table, which by now you've probably memorized, right? And you're going to need to memorize that for the final. Not just kidding, you'll have it available to you, so don't worry about that. Okay, the first topic of the day goes like this. I want to give you the ability to predict in which direction a spontaneous will be good. Okay, so let's consider this one where potassium with silver nitrate forms potassium nitrate plus silver. Okay, now, first of all, to simplify these, you want to eliminate any spectator ion. Now, the reason I put the word spectator, it may not be exactly the ones I listed as spectators with you before, but here's how you can eliminate the spectator ions. Look for any chemical or group of chemicals that is not changing their oxidation state. Notice they look the same on both sides. So, for example, notice potassium's alone and then it is in a compound, so it's not a spectator. Same thing on the silver. It's in a compound and then is alone, it's not a spectator. But notice nitrate is the same on both sides. So therefore, it'll be easier to analyze if you eliminate the spectator and get down to the guts of the reaction, which is just potassium plus silver ions, gives you potassium ions plus silver. I'm going to show you two methods of figuring out how the reaction is spontaneous. Now, method number one goes like this. Break this up and make it an electrochemical cell. So that's where you want to use your half reaction charts. So potassium goes to potassium plus. If you look on your chart, and that's the second one from the top, it would have a voltage of 2.9 volts. Okay, now you got to look way down to find the silver one, and notice the silver one, we're stuck with this, the reverse of on the table. So about 3/4 of the way down, you see the silver half reaction. I reversed it, and when you reverse the half reaction, you reverse the sign, make it in positive 0.8. So you algebraically add the two together, and notice I get a positive voltage. So when the voltage is positive means the way the reaction is written, it is spontaneous. So this is one method of doing it. And by the way, notice you could actually care less what the actual number is. It's a sign that counts. A positive sign means spontaneous reaction. So that's method number one. I'd like to now show you my favorite method, method number two, which I entitle electron pushers. So method number two, okay, I call it electron pushers. Okay, so we're looking at the guts of the reaction. Now, remember that the table I passed out to you is a list of oxidations, and the Berg term for that is they're called electron pushers. In other words, look at every single half reaction, and you notice they're producing electrons, they're pushing electrons. Okay, so what you want to do is see which one's the better electron pusher. So look on the left-hand side of the reaction, and you will see that potassium is a pusher. It's on the left-hand column of the half reaction table. So it is a pusher, and it's trying to push electrons onto silver. Okay, same thing. If you look low on the chart, about 3/4 way down, you'll see that silver is also an electron pusher, and so it's trying to push electrons onto potassium. Okay, so here's the two electron pushers. Now they're in competition with each other. That's why I show the arrows where potassium is trying to push electrons onto the silver, and silver trying to push electrons on potassium ions. So now you want to look in the chart and see which one is higher on the chart, because that'll be the better electron pusher. And no contest, potassium is a better electron pusher than silver, and for that reason means potassium is going to win, and therefore the reaction is going to go from left to right. So that's how you tell the reaction will be spontaneous. So I personally like the electron pusher method. I think it's faster. So again, what you do is you compare the two electron pushers and see which one is the better one, and then which one's going to win the contest for pushing electrons. Now, for example, if silver was the electron pusher, silver would win, the electron would go from right to left. Okay, so let me give you a moment to try this next one on your own. So it seems to me step number one is, why don't you eliminate the spectator? And how do you tell which one's a spectator? If it looks the same on both sides, in other words, it's in a compound on both sides, it's probably going to be a spectator. So the gold goes from being alone to being a compound. It's going to be changing. Same thing on the sodium. So it looks like the chlorine must be the spectator. Okay, so you've had a chance to try that. So let's see what the next page looks like. Let's see if you did it correctly. Okay, so how did you guys do? So gold's trying to push electrons onto sodium, and sodium's trying to push electrons onto gold. Okay, so you look on your chart, and which one's a better electron pusher? Again, no contest. Sodium is going to win. It's going to push the electrons onto gold, and it's going to beat out gold trying to push electrons onto sodium. Okay, so since sodium's the winner, and it's on the right-hand side, it gets to react, so therefore the reaction is spontaneous from left to right. By the way, notice you can really learn some interesting things from the reaction. So if you put your gold ring into table salt, you just found out there's no reaction, okay? So it's safe to do that. Okay, try this next one on your own a little bit harder. I think the hard part is to find the spectator in this case. So once you find the spectator, eliminate it, and then look at the two electron pushers and decide who's the better electron pusher. Okay, so I put the spectator in parentheses. So notice sodium looks the same on both sides. It's in a compound on both sides, whereas the chlorine goes from compound to being alone, and the iodine goes from being alone to being a compound. Yeah, so it must be a fight between chlorine and iodine as to who's the better electron pusher. Okay, so look really low on the chart, and notice you'll find chloride ions, that's the fourth from the bottom, and iodide ions, which is about a quarter of the way up, okay? And iodine is higher, so it gets to be the pusher, and chlorine does not. Okay, so if iodide wins, that means that it's going to be the pusher, and therefore it's the reactant, and therefore the reaction goes from right to left. By the way, this reaction is actually used in the laboratory to identify iodine. So what happens is you think an iodide compound, let's say sodium iodide, and you take some chlorine water, add it, and if the reaction takes place, if there is iodide present, you get iodine, and iodine, when it's in hexane, is a purple color, so it's really kind of a cool test. And we would have done that if we would have had lab. Okay, so look at problem D now. Why don't you try problem D?
Professor, I have a question.
Yes.
How do you know which way the reaction goes?
Okay, the way the reaction goes is which one gets to be the reactant.
Oh.
Okay. So iodine is the winner, which means it gets to be the reactant. Now, if it gets to be the reactant, it means it's going to react, which means if it reacts, it's going to make the reaction go the other direction. That makes sense?
Yeah, that does make sense. Thank you.
So I guess the best words I use is reactant. So if it's the reactant, that means it's going to start the reaction and it goes away from it.
Okay, got it.
So I hope that, good question. So I hope that kind of makes sense. Okay, reaction D. So again, to make it less complicated, see if you can eliminate the spectator. So look for the chemical or group of chemicals that looks the same on both sides. And if you do that, you should come up with the nitrate being the spectator, and I put it in brackets. Okay, so now it's a fight between zinc wants to give up electrons to hydrogen, and hydrogen wants to give electrons to zinc. So look on the chart and see who is higher on the chart, who's the better electron pusher, who gets to be the reactant, zinc or hydrogen. It looks to me like zinc is about a quarter of the way down on the chart, and hydrogen, notice, is nicely mixed, it's in the middle. So zinc is a better electron pusher, it gets to be the reactant. Okay, so therefore the reaction is the reactant is on the left and it goes to the right hand side. Joanna, does that seem okay?
Yeah, that does make sense.
Good. Okay, now I'd like you to look at something else that's kind of interesting. Do you notice they marked hydrogen very dark on your chart? The reason they did that is because any metal higher than hydrogen will push electrons on hydrogen. It means any metal above that will react with an acid. Notice that the reaction has nitric acid. So any acid above there, from lithium all the way to lead, they will react with acid. Now, what do you think it means about the metals below hydrogen? Ooh, they would not react with acid because hydrogen would be a better pusher of electrons than those metals. Kind of isn't it? So that chart is really good to tell you which chemicals react with acids and not. Okay, you're about to see superkiller. Okay, superkiller goes like this. Okay, so lithium fluoride gives you lithium and fluorine. So let me give you a moment on your own to see if you can figure out which way this reaction is spontaneous. Now, what you should have noticed by now is, there's no spectator. How do I know that? Because lithium in a compound is going to go lithium alone, and fluorine in a compound is going to go fluorine alone. Wow, no spectators. Now the tricky part is, remember, your handy dandy chart shows the electron pushers on the left-hand side. So look at lithium, half reaction, okay? And what you need to do is look at which form of lithium is the pusher, and look at the very bottom of the chart and see which form of fluorine is the pusher. Okay, so here comes the answer. Okay, so lithium alone is the pusher. Okay, so that's why I have the arrow going from lithium to fluorine. And if you look at the bottom, fluorine with a negative charge, which is what it would be in a compound, so fluorine in a compound is the pusher. So the fight between lithium and fluoride, and no contest. No, lithium is definitely the winner. It gets to be the reactant. So if it's going to be the reactant, the reaction is going to go from right to left. By the way, I want you to notice that I have picked the best pusher with the worst pusher. Okay, or I guess you say I put it with the best pusher with the best acceptor, which means a lithium fluoride battery would be very, very powerful. I think they purposely don't make it. It's so powerful it actually explodes, so it gives off too much heat. But it would be a very powerful battery. Okay, now I've done the next one with you. So let's just analyze and see if I did it correctly, okay? So copper metal with silver nitrate, and on the right-hand side, silver with copper nitrate. Okay, so the spectator, I think you agree, would be the nitrate, and the ones that are changing is copper alone to copper in a compound, silver in a compound to silver alone. So it's a fight between copper metal and silver metal. They're both on the pusher side. They're on the left-hand side of the chart. And notice that copper is higher than silver. So let's see. They're both on the lower part of the chart, but copper is about 4 down from hydrogen, and silver is way down there. It's about 3/4 of the way down. So I think you agree, copper would be the better reactant. Okay, so therefore, copper would react with silver nitrate. Now, if we were in the classroom, I would have done this as a demonstration for you. Sorry, I couldn't do it. So the best thing I could do is find a picture of this, but I want to see if the picture actually makes sense to you. So what you're looking at is you're actually looking at a coil of copper that's now coated with silver crystals. So the product will be the silver crystals. You don't actually get to see the copper is coated. And notice the solution is kind of blue in color. And that means some of the copper metal is dissolved because copper in solution is kind of a blue color. So it's kind of a neat reaction of how you can actually make silver. Okay, take a good look at this reaction because the next chart is going to show the reaction in reverse because I want to talk about reversing the reaction. Okay, so notice I've written the reverse of the reaction, and notice I put a slash because that reaction does not take place. Why is that? Because copper can give electrons to silver in solution, but silver cannot give electrons to copper in solution. Okay, so that is a non-spontaneous reaction. Now, it's always bothered me in chemistry when we have that slash because it says, no, that reaction cannot take place. I like to be able to do everything in chemistry, okay? So really what the slash means is the reaction will not occur on its own. It will not occur spontaneously. Now, actually why that is, I've drawn a little energy diagram. That's because silver and copper nitrate are at a lower energy level. They're more stable, and copper and silver nitrate are at a high energy level. In other words, for this reaction to take place, you got to put energy in. It's an uphill battle. Now, what form of energy could we possibly use? I guess we could use light. I wonder if anybody's ever tried that. We could use heat, but what do you think we're going to use since the topic of the course is electrochemistry? Yeah, we're going to use electricity. Okay. Now, the statement below, by the way, why don't you correct my mistake there? It's supposed to say there must be a way of forcing this reaction. Okay. So far we've actually used chemical reactions to make electricity. Now we're going to get to the last part of the course. We're actually going to use electricity to force a chemical reaction to take place.